Hello, my name is Achirawich Phongpanich.
My name is Kanisorn Kanokratana.
Today we are going to present about our project RogueType AI-enabled typing game. Let's start with the problem statement, which is the traditional typing games using statistic difficulty levels result in player boredom or frustration. The goal is to personalize the game experience by dynamically adjusting word difficulty based on real-time player performance. For the business objectives, the personalized gameplay with adaptive difficulty, increasing player engagement and retention, provide meaningful learning progress by challenging players at the right skill levels. For the input data requirements, we use wave numbers, which is the current level of waves, combo length, which is the consecutive correct word per minute from players' timing speed, mistake count from the number of errors in the current wave, and lastly, the recent accuracy, which comes from the last n word from 0 to 1. The model selection and justification, we select the logistic regression for lightweight and fast for real-time gameplay, high baseline performance, which is above 90% accuracy, and also compatible with offline environments. In the preprocessing and training, we use normalizing numerical input with standard scalar, about 80 per 20 training validation split. For the training configuration, we use multi-class equal to multi-nominal. Max iter is 500 and the zero as model PKL and scalar PKL for deployment. For the evaluation metrics, the validation accuracy is 90.5%. The model accuracy is above 85%. Player experience improve every session duration. Explainability, we use the sharp analysis. And stability, we use minimal fluctuation response. For the model training implementation, to identify the most sustainable logistic regression configuration for RogueType's adaptive difficulty system, we conduct 3M flow track experiment with very hyperparameters. In the run 1, we use brushing strut 653, which use the default logistic regression settings, yielding a solid validation accuracy of 0.88. In the run 2, we use White Dolphin S02 to adjust the regularization strength to C equal to 0.5 and increase max iter to 1000. This achieved the best result with 0.89 accuracy. For the run 3, we use Pen Strike 477 to apply stronger regularization with C equal to 0.3 and max iter equal to 2000. But the performance dropped slightly to 0.86. All experiments were tracked using ML4, including log parameters, metrics, and models. In the conclusion, we select run 2, which is the White Dolphin A02 as the final model, due to the highest accuracy, stability, and efficient convergence. To interpret the decision made by trained logistic regression model in RogueType, we apply SHARP, a game theory-based framework for explaining individual predictions and feature importance. We use the SHARP to explain API to compute sharp values on the validation set. Since our model is multi-class logistic regression, Sharp generate impact values for each class. For example, like 0 is the easy, 1 is the medium, and 2 is hard. Then we generate a sharp summary plot which visualizes the average impact of each feature across all classes. WPM is the most influential feature in predicting difficulty due to higher WPM push toward harder levels. Recent accuracy and combo length mainly contribute to medium difficulties predictions. Mistake count and wave number have smaller but still meaningful effects, especially when the model is uncertain. For the prediction reasoning, although the player had high word per minute and a decent combo, the low mistake count had a much stronger positive influence on predicting hard difficulties. These mixed signals led to Barnes' prediction slightly favoring the hard class. For the example case 2, the player's low word per minute and short combo length heavily influenced the model to predict an easy class. Even though the mistake count was only slightly high, it wasn't enough to counterbalance the sign of struggle. And here's the example case number 3. Despite having a high word per minute and a strong combo, the player's roll mistake count had a biggest influence, shifting the prediction away from easy and toward harder difficulty. The result leans toward class 2 due to minimal errors. And here is our model deployment as a service. We create a fast API app with posts the predict. And this is our sample data. As you can see at the bottom right, the result is the predict difficulty equal to 1.
Okay, so we come to the UI model integration. In this section, we focus on how the AI model integrates with the user interface in real-time gameplay. So the model analyzes player performance to adapt both word difficulty and enemy spawn rate dynamically. This makes the game feel more responsive and personalized for each player. So we come to the UI design for adaptive gameplay design. First, during a gameplay, we continuously monitor 5 key metrics: word per minute, combo streak, mistake count, recent accuracy, and wave number. So those metrics are sent to the model via a RESTful API, which predicts a difficulty level from 0 to 2. Based on the prediction, the game selects a word from easy to hard, and it also scales enemy spawn rate, spawning more enemy for skilled player and fewer for stalker 1. And here is a sequence diagram. So first is that the game collects performance data and it sends that data to the model via post. So the backend validates and scale the input, and the AI model predicts the difficulty, and the prediction is returned to the UI, and the UI adjusts the word and enemy difficulty accordingly. So we come to the UI to model API request. So the interface uses a simple post request to communicate with the model. The JSON payload includes word per minute, combo length, mistake count, recent accuracy, and wave number. So the model responds with a predict difficulty level. Again, it's at 0, 1, or 2. This response updates both the word difficulty and enemy spawn configuration. So we come to the challenge and solution. One of the big issues was a mismatch field name between the UI and backend, which caused error. To fix this, we standardize field name and add a validation to handle bad input gracefully. This ensures smooth configuration between the model and game even when something goes wrong. And that's all for our presentation. Thank you.